All right, boys and girls, welcome back to the drive-thru for a special ice-cold edition brought to you by the deli. Welcome to the second semester. The second semester is brought to you by the deli. Hungry? Stop by and get yourself some beef stew. All right, so this is 13-4. We're going to try to do 2 videos on this, if necessary. The first one's going to be kind of basic, and we're going to explain mass and center of mass and moments of inertia. And then the second video we'll come back and do some problems from the section tomorrow, if indeed we have school tomorrow. All right, so a couple things. For 13-4, we are dealing with centers of mass and moments of inertia, 2 awesome topics. But the strange thing about this is we're doing it all for what's called a planar lamina, okay? And basically, think of a planar lamina as like a 2-dimensional object. However, it has like a uniform thickness of 1 unit. So think about it like a piece of paper, maybe. I mean, you know that like maybe we imagine paper to have no thickness, but if you stacked 500 pieces of paper up, you'd have a height, and it would have a volume. Okay, so if we can understand how we're going to find mass and centers of mass and moments of inertia for planar lamina like this, then later on in the chapter, when we start to deal with 3-dimensional figures, we'll have a much easier time understanding the process of doing that in 3 dimensions. Okay, so before we get into anything, I want you to think about center of mass. Imagine, okay, Mr. G and Mr. U are on a teeter-totter together. And Mr. G was tired and sick of being smart, so he left it up to Mr. U to figure out where to put this fulcrum so that we can have an enjoyable experience on our teeter-totter ride. Okay, so you could imagine that the distance between the fulcrum and Mr. G would have to be significantly greater than the distance between the fulcrum and Mr. U. Okay? So let's think about how we would calculate that center of mass. If this was my position, x1, and this was the average position, x bar, and this was Mr. G's position, x2, okay? We would have to say that my mass times my distance, positive, so I'll do x bar minus x1, would have to be equal to Mr. G's mass times, and now I'll do x2 minus x bar, again, to keep that positive. And that would have to be true in order for our system to have some balance, okay? So if we wanted to find out what x bar was, we would distribute m1 x bar minus m1 x1 is equal to m2 x bar minus m2 x2. I got that backwards. So m plus m2 and minus that, right? Yes, okay. So let's clean that up here. So if we moved everything over and cleaned it up and solved for it, we would end up getting x bar is equal to m1 x1 plus m2 x2 over the sum of our masses. Okay? So that's how we would find our position x bar. So, like, to summarize, we are taking the products of our masses and our positions, adding them, and dividing by the total mass. Hopefully you guys can feel the integrals coming. But we're going to come back to that because first we want to talk about mass. Okay? So now let's imagine that we've got a region. Okay? But in this region, and this region we're going to turn into a little planar lamina. So it's just an area that we're going to treat like an area. But it's got a uniform height of 1 unit. So this thing actually technically has volume, but the volume, the number of the volume, or the magnitude of the volume will be the same as the magnitude of the area because it's a lamina and it's just 1 unit wide, okay? So that's the hard part of this. Hopefully in class we'll get that settled. Well, let's say this thing had variable density. Okay, so it was a lamina that was made up of maybe some melted ore, and it displaced more of the mass in one spot than the other. And so that's going to be what our task is. Well, you could imagine, hopefully, that this mass of this object is, well, the mass of any object is usually volume times density. For today, the mass for 13.4 is actually going to be area times density, and that's going to be weird for anyone that loves physics. They're going to hate that. But since our volume of a lamina is really the area times 1, that's how our book chooses to explain it, and you guys are following along in the book, so we're going to go with that, okay? Well, since this thing has variable density, okay, then we're going to need an integral to add it up. So our mass is going to be the double integral, because the double integral gives us this area, dA, remember that could be dy dx, dx dy, or eventually it could be dr d theta, or, you know, hopefully you get that. Now what's in here? In here is now rho, what we'll call rho of xy. I think that's a rho. Looks like a cursive P. And all we're talking about here is now we don't have a height over this. We're not calculating volume. This right here, this function is a density function. Okay? And that controls the variable density throughout this area. So this is our mass equation. Okay? So that should lead us, if you remember from our last slide, that our x bar, which is our balanced position, is basically the product of mass times position over the sum of the masses. Okay? What we're going to want to do is to find our center of mass. That's just going to be x bar, comma, y bar, okay? So, but our x bar is going to be the double integral over a region, okay, of x, our position, times rho of x comma y, our density dA, divided by our mass. So just the double integral of rho of x comma y dA. That's just our x bar. So we take our position, okay, times our mass, and we divide it by the sum of our masses. Let's compare that to the first slide. Position times mass, we're going to add them all up, which is an integral over the sum of the masses. So that definitely holds true. So our y bar will be the double integral over a region of y times the mass. Mass is, in this case, area times density, all over just the mass. Okay? So to find the center of mass, we've got to do all of this, and now maybe you're starting to understand why we're going to use our calculator to do so much integration, or else we're not going to get much done. Okay? Okay, now the final piece of this section that I'm going to introduce to you in this video is about the moments of inertia, specifically the second moment of inertia. And they call it the second moment of inertia because of this r squared. I equals m r squared. This is our second moment of inertia. Okay, so what that tells us is that something's willingness to rotate about a point or about a line, once we get into 3 dimensions, is dependent on the mass of that thing and the amount of distance between the r between that thing and the point of rotation. So again, you can kind of imagine how this is going to be pretty complicated when we have a variable mass within an object, which is again why we're just starting today with 2-dimensional planar laminas. Okay? So that just says that something's, well, I'm not going to repeat it. I don't know it well enough to repeat it. I can't put it any other way. Luckily, you'll be doing this in physics in the next 2 weeks, but I want you to just think about it as it will take more energy to make something rotate if it's further away from the center. I think I said that right, but let's just go in and look at the equation, and then we'll have a good discussion on this in class. And whatever we don't understand, we'll just go ask this guy. And luckily, he's a good guy, and he'll help us. All right, so if you think about where this is going, maybe you can kind of predict what these moments. So instead of x bar and y bar, now we're going to have mx comma my. Okay, and those are the moments used let's back that up. Excuse me. Those would be our first moments. That's the same thing as the center of mass. So that's the same thing as x bar and y bar. Let's call this Ix and Iy. That's the moment of inertia with respect to x and the moment of inertia with respect to y. Well, if we understand this, then we should be able to go from there to an integral, because we know what mass is. Okay, it's the double integral over a region of the density function dA. So now what do we want to multiply it by? Well, we want to multiply it by r squared. Well, how far is r from the x-axis? So here, this is Ix. How far is r from the x-axis? Well, it's however many y's it is. So now our r becomes y, and that becomes a y squared. Okay? How far is something away from the y-axis? Well, in this case, since we're working in 2 dimensions today, that's going to be x squared. And here we have our formulas for the moments at a given point. All right, so we're going to stop there. You've got your formulas. That should be enough to get you started. As you work through these examples, hopefully you always look at your answer and make sure that it makes sense. You should interpret the variable density and envision to yourself, where would the majority of this weight be distributed? And then think about how that would affect the center of mass and the moment of inertia, the desire to rotate. And I've hit my limit. I miss you guys, but gosh, I wouldn't mind not seeing you one more day. Get a little snow day. I'll settle for a delay, but if I see you tomorrow, we'll have a great day. I just may. Give me some hay. Boom!